In this video we will show that for any integer m greater than 0, the product m times m plus 1 cannot be square of any integer. First solution of this problem, which we consider, is as follows. First, we suppose that initial statement is wrong, so m times m plus 1 can be the square of some integer. We denote this integer n, where n is greater than 0, and analyze the equation 1. First, we remove here 1, so we decrease left-hand side. On the left we will have m squared, so we can write that m squared is smaller than n squared. We return to equation 1, and now we replace m with m plus 1. So on the left we will have m plus 1 squared, so we increased left-hand side, and we can write that m plus 1 squared is greater than n squared. So we will use these inequalities, and we can write that first m squared is smaller than n squared. From the other side, n squared is smaller than m plus 1 squared. Now we take square root from all parts of this inequality, and we have the following. N is greater than m, and n is smaller than m plus 1. It means that n is between two consecutive integers, and so it cannot be an integer. This is in contradiction with our initial statement here, so we prove our theorem. So m times m plus 1 cannot be the square of any integer. Now it is instructive to consider the second solution of the same problem. This solution is a little bit more complicated than the first, but it's very useful to consider it. It is based on the same supposition that m times m plus 1 is equal to square of some integer. Again, we denote this integer as n, and n is greater than 0. And then we rewrite this equation as follows. First, we multiply m with what is inside the brackets, so we will have m squared plus m equal n squared. And then we do the following. We rewrite m as 2 times 1/2, this is 1, actually coefficient at m, times m, and we add to the left-hand side and to the right-hand side 1 over 2 squared. So on the right we will have n squared plus 1/2 squared. Next we take this equation and apply to the left-hand side the well-known formula of algebra. So we will have here m plus 1/2 squared and equal n squared plus 1 over 4. Next, we move n squared to the left. We obtain this equation, and we will use some simplification. We take here, instead of m plus 1/2, we'll write 2m plus 1 over 2 squared, and this is equal to m plus 1 squared over 4. We replace this part with what we get here, minus n squared equal 1/4. We go further And to equation which we obtained, first we multiply by 4 both parts of this equation. We will obtain 2m plus 1 squared minus 4n squared equal 1. Again, we rewrite this equation in such form. Instead 4n squared, we will write 2n squared equal 1. And we apply another equation of algebra, a squared minus b squared equal this one. So we will have here the following. We will have here the product of these two terms, 2m minus 2n plus 1, 2m plus 2n plus 1, it is equal 1. And now we will think what we have got. So here is an integer, here is again an integer, and the product of two integers equal 1. We know for sure that this integer is positive. This integer can be positive and negative, but nevertheless, to get 1, we need to have here 1 and here 1. So we have two equations. This equation, 2m minus 2n plus 1 equal 1, and another one equation. We can consider these two equations as a system. We can cancel 1 here, 1 here, 1 here, 1 here. So we get the following. We have another system which has this form. This equation has only one solution, m equal n equals 0. So for us, most important that m is equal 0, but our initial, what we supposed was that m is greater than 0. So we again came to contradiction. It means that our statement that the product which we consider equal integer square is not correct. And we can write that m times m plus 1 not equal to square of any integer. So this is a final step of the second solution. If you like this video, you may want to click like button, leave a comment and subscribe for the channel.